From the moment early humans looked upward and saw the birds gliding through the open air, a quiet jealousy was born. The ground felt safe, but it also felt like a cage. The pull that kept their feet pressed to the earth seemed both comforting and cruel. It was gravity, the invisible tether that allowed the moon to orbit, the rivers to flow downhill, and the apple to fall straight instead of sideways. Yet it was also the force that denied us the sky. For thousands of years, humanity's imagination was filled with stories of those who escaped its grip. From the myth of Icarus, who dared to fly on wings of wax, to the dreamers of the Renaissance sketching machines that might one day lift man above the clouds. Every era carried its own rebellion against gravity, a declaration that the human mind would not be limited by what nature decreed. When the first balloons lifted from the ground in the 18th century, spectators thought they were witnessing magic. It was as if someone had torn a hole in the laws of nature. Then came the age of flight. Engines roared, wings cut through the air, and the once impossible became a matter of engineering. But these triumphs, as miraculous as they seemed, were not true victories over gravity. They were clever evasions. The airplane did not change the pull of the Earth. It simply balanced against it. It fought gravity with lift, trading energy for time in the sky. When the engines stopped, gravity always won. The 20th century brought a new kind of defiance. Rockets burst from their launch pads, flames pushing downward as metal soared upward. Humanity left the atmosphere, reached the moon, and built machines that now travel beyond the edge of the solar system. Yet even in these greatest of achievements, gravity remained undefeated. The rocket did not master gravity, it only overpowered it for a brief and costly moment. Each launch was an act of brute force, a temporary escape rather than control. Every spacecraft that rises must one day fall, every orbit decays, and every astronaut must eventually return to the embrace of the planet's pull. To speak of controlling gravity is to imagine something profoundly different. It is not about resisting or escaping it. It is about altering it. True control would mean shaping the field itself, deciding how strong gravity should be, and in what direction it should act. It would mean turning the universe's oldest law into a tool, as humans once learned to harness fire or electricity. Imagine being able to reduce the pull of the Earth with a switch, or generate your own gravity field to anchor a ship in deep space. Such control would not merely change how we travel, it would change what it means to exist within spacetime. The dream of controlling gravity exposes a curious paradox. Humanity has learned to manipulate almost every other fundamental force. We can command electricity to flow through circuits, bend magnetism into precise fields, and unleash nuclear energy from the heart of atoms. We have transformed electromagnetism, a mysterious phenomenon once feared and misunderstood, into the foundation of civilization. Yet gravity, the very first force we ever experienced, remains beyond our touch. It shapes galaxies and bends light across the cosmos, but no experiment, no device, no laboratory has ever managed to create or cancel even a whisper of gravitational change. This paradox fascinates and frustrates scientists. Why is gravity so utterly different? The answer lies in its nature. Every force we can manipulate seems to come in pairs. Electric charges attract or repel depending on polarity. Magnetic poles push and pull with elegant symmetry. Gravity, however, only attracts. There are no negative masses, no north and south poles of gravitation. It pulls everything toward everything else, endlessly, without cancellation. Its strength may be weak compared to electromagnetism, but its reach is infinite. Because every particle with mass contributes to it, gravity becomes the one force that cannot be screened or blocked. You can hide from light by stepping into a shadow, but you cannot hide from gravity. Visualize the symbols of this paradox: the falling apple, the shuttle lifting from its launch pad, the curved orbit of a satellite, and the invisible grid of space-time bending beneath massive planets. These are the manifestations of one grand phenomenon that we understand yet cannot command. The sight of a rocket clawing through the atmosphere is a reminder of how much energy it takes just to momentarily oppose gravity's rule. Every grain of sand, every drop of water, every cell in our bodies participates in this cosmic handshake that connects us to the Earth's center. And yet, the human spirit is not content with acceptance. We do not simply want to coexist with gravity. We want to master it. We want to bend it, to shape it, to turn it into something we can engineer. This desire comes not only from curiosity, but from survival. Our future beyond the Earth, the dream of living on other worlds, depends on learning how to manage gravity. Artificial gravity for long-duration spaceflight, stable orbits for vast habitats, propulsion systems that no longer rely on explosive fuel. All of it hinges on understanding gravity at a level we have not yet reached. But before we can dream of controlling gravity, we must first confront what it actually is. Is it truly a force that pulls us downward, or is that an illusion created by something deeper? Centuries of observation have revealed its behavior, but its essence remains elusive. Humanity has stood on this boundary before, at the edge of the known, staring into the unknown, asking whether our perception of reality is complete. The story of gravity is not just a story of falling apples and rising rockets. It is the story of how we came to see the invisible scaffolding of the universe itself. To control gravity, we must understand it not as a chain that holds us, but as a fabric we might one day weave. And that means beginning with the most fundamental question of all: what is gravity, truly? The story of gravity begins long before rockets and relativity. It begins with a simple observation repeated endlessly through human history. Things fall. An apple slips from a branch. A stone drops from the hand. Rain descends from clouds. The pattern is so consistent, so unquestionable, that it became invisible to thought. For most of human existence, gravity was not seen as a mystery, but as a fact of nature, unquestioned like breath itself. Yet as human curiosity matured, that falling apple became the symbol of awakening. It was a sign that even the most ordinary motion could reveal the deepest secrets of the cosmos. When Isaac Newton looked at the falling apple, he did not simply see it fall. He asked why. What invisible hand pulled it downward? And could that same hand be reaching out across the heavens, guiding the moon around the earth? His answer changed the world. Newton proposed that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of their distance. It was a revelation that united heaven and earth under one law. The same principle that caused the apple to fall kept the planets in orbit. For the first time, gravity became a universal connection, a single thread weaving together the entire cosmos. This was not just a scientific breakthrough, it was a philosophical earthquake. Newton's law transformed the way humanity understood the universe. The sky was no longer a separate realm governed by divine perfection. It was a continuation of the same physical world we inhabited. The heavens obeyed the same mathematics as a pebble rolling down a hill. The cosmos became intelligible, predictable, and measurable. The great clockwork universe had been born, yet Newton himself sensed that something about his discovery was incomplete. He could calculate the force of gravity, but he could not explain its cause. How could one object act upon another across empty space with no visible connection? He admitted, with rare humility, that the mechanism was beyond his understanding. Hypotheses non fingo, he wrote. I frame no hypotheses. Gravity worked, but no one knew why. For centuries, Newton's law reigned supreme. It guided the paths of comets, the design of bridges, and the mechanics of every moving thing. It carried humanity through the industrial age and into the dawn of spaceflight. But as observations grew more precise, small cracks appeared in the theory's perfection. The orbit of Mercury, for instance, refused to match predictions. Light, though massless, seemed to bend slightly near massive bodies, as if affected by gravity. Something deeper was hiding beneath the equations. Then came Albert Einstein. At the dawn of the 20th century, he reimagined the universe not as a clockwork of invisible forces, but as a flexible geometry. Gravity, he proposed, was not a pull acting across space. It was space itself, curved, distorted, shaped by the presence of mass and energy. Planets orbit stars not because they are pulled by a distant force, but because they move along the natural paths within curved space-time, like marbles rolling along a warped surface. The apple does not fall because it is tugged downward, but because the fabric of space-time guides its path toward the Earth's center. This vision changed everything. What Newton had described as a force was revealed to be the manifestation of geometry. Matter tells space-time how to curve, and curved space-time tells matter how to move. The simplicity of that sentence hides its profound depth. It means that to control gravity, one would have to control the shape of the universe itself. There is no gravitational switch to flip, no field to generate or cancel. The phenomenon we experience as a pull is the way space and time behave in the presence of energy. To understand this, imagine a vast elastic sheet stretched tight. When a heavy sphere is placed on the sheet, it sinks slightly, creating a dimple. Smaller spheres rolling nearby will spiral inward, not because they are being pulled, but because they are following the natural curves of the surface. The heavier the sphere, the deeper the dimple. In this simple metaphor lies the key to modern gravity. What we call the gravitational field is nothing more than the curvature of space-time caused by mass and energy. This insight explains why controlling gravity is so much harder than manipulating electricity or magnetism. When you turn on a magnetic field, you are rearranging the behavior of particles within space. But to alter gravity, you must alter space itself. The structure of space-time is not something external that can be pushed or twisted easily. It is the stage upon which all events occur, including us. The stage cannot be lifted from within by ordinary means. Einstein's equations describe this relationship with elegant precision. In their symbolic form, they state that the geometry of space-time, represented by a mathematical object called the Einstein tensor, is directly related to the distribution of mass and energy, represented by another object known as the stress-energy tensor. In essence, the more energy you have in a region, the more curved space-time becomes. This curvature dictates how objects move, which we perceive as gravity. The implications of this are staggering. To truly manipulate gravity would require manipulating the very geometry of existence. It is as if you wish to sculpt a mountain, not by moving earth and stone, but by adjusting the underlying coordinates of the world. The scale of energy involved in bending space-time even slightly is almost unimaginable. Every object, from a planet to a galaxy, already curves space-time naturally, but to do so deliberately would demand energies far beyond anything we can produce. And yet, Einstein's theory did more than close the door on easy control of gravity. It opened new ones. It revealed that space-time itself is dynamic. It can stretch, ripple, and evolve. It can carry waves of curvature across the cosmos, and those waves can be measured. The discovery that gravity is not a static force, but a living geometry, transformed our understanding of the universe. It means that, in principle, space-time can be shaped. The question is whether that principle can ever be turned into technology. The human dream of defying gravity thus becomes a question of engineering the very fabric of reality. To do so, we must learn how curvature responds to energy, how the presence of mass alters geometry, and whether other forms of energy might mimic the same effect. In the next steps of this exploration, the focus will shift from understanding gravity's nature to understanding the energy that gives it form. Because if mass and energy are the source of curvature, then controlling curvature must begin with controlling energy itself. The universe writes its structure in energy. Every mountain, star, and atom is a note in a cosmic equation where energy and mass compose the melody of curvature. In Einstein's vision, gravity is not a separate tune, but the rhythm of that melody itself. The relationship is beautifully simple and impossibly demanding. The greater the energy density in a region of space, the more that region curves the fabric of space-time. The result of that curvature is what we feel as gravity. If we wish to control gravity, we must learn to play that rhythm deliberately, to add or subtract curvature by arranging energy as skillfully as we now arrange electricity. But nature guards this secret behind immense scales. To bend space-time noticeably, even by the smallest degree, demands energy so vast that it borders on the absurd. To curve space-time by only a fraction of a percent across a region the size of a house would require the equivalent energy of an entire planet. That is not an exaggeration. It is a reflection of the cosmic stiffness of space-time. The universe itself bends easily because it deals in galaxies and black holes, where masses reach into numbers that defy language. A human laboratory, even with all the power of civilization, produces energy that is microscopic in comparison. To understand why, imagine space-time as a fabric woven from threads finer than anything we can perceive. The threads are so tightly interlocked that changing their shape requires unimaginable force. When the Earth pulls objects toward its center, it does so not by emitting a field, but by shaping the geometry of the space around it. Everything within that geometry simply follows the natural paths available to it. The deeper the Earth's curvature, the stronger the apparent pull. To alter that curve, to flatten it or reverse it, would mean pushing against the weight of the entire planet's geometry. We already know that massive objects bend space-time, but energy alone can do the same. Light itself, though massless, carries energy and thus contributes to curvature. In theory, an intense beam of light can warp space-time as it passes, though the effect is infinitesimally small. Only in the most extreme environments, near black holes or in the heart of supernovae, does energy reach levels where its gravitational effect becomes visible. The stars themselves are the universe's natural laboratories for gravitational engineering. Every time a star ignites, it demonstrates how energy sculpts space-time into stability. This understanding leads to a sobering realization. The control of gravity is not a matter of clever machinery or magnetic tricks. It is a matter of cosmic energy management. If one could somehow gather and direct energy with perfect precision, one could, in principle, bend space-time as desired. But the required energy densities would dwarf anything we can currently produce. Even our most powerful particle accelerators, which collide subatomic particles at nearly the speed of light, barely graze the edges of the curvature they generate. The energy released in those collisions is enough to create new particles, but not enough to warp space-time beyond the smallest imaginable scales. There have been imaginative suggestions that perhaps there are shortcuts. Some physicists have speculated about using exotic forms of matter, substances with negative energy or unusual pressure, to produce curvature without immense mass. Such materials remain purely hypothetical. None have ever been detected in nature, and no experiment has yet created them. The universe, as far as we know, contains no convenient way to bend its own fabric cheaply. Even the dark energy that accelerates cosmic expansion operates on scales so vast and diffuse that we can only observe its effects indirectly. Still, these questions matter deeply because they redefine what it would mean to control gravity. It would not necessarily require brute strength, but understanding. If gravity is geometry, then perhaps one day we could manipulate that geometry through indirect means, through quantum processes, through the organization of information, or through effects we do not yet recognize. After all, the leap from Newton's force to Einstein's curvature was itself a revolution in perspective. The next leap may be just as profound. When we look at the curvature of space-time around massive bodies, we are seeing the language of the cosmos written in shape rather than sound. The paths of planets, the bending of light, the rhythm of orbits, all of it is geometry speaking through motion. Every time you drop a ball or see the moon rise, you are watching energy curve space and time into a seamless whole. The dream of controlling gravity is therefore the dream of writing new lines into that geometry, to compose new motions in the fabric of reality. Yet, as impossible as that seems, Humanity has always lived on the boundary between the impossible and the inevitable. We once thought heavier-than-air flight could never be achieved. We once believed the sound barrier was an immutable wall. We once imagined the stars as unreachable points of light. Each of those barriers fell when understanding caught up with imagination. The question of gravity may follow the same arc. To control it may take centuries or millennia, but knowledge has a way of bending reality itself. The quest now turns from the scale of planets to the scale of particles. For if gravity arises from the energy and geometry of space-time, then perhaps its secret lies in the smallest building blocks of nature. Somewhere beneath the equations of curvature, at the border where quantum mechanics meets relativity, there may exist the key to bending space itself. The next step in our journey takes us to that frontier, to the mysterious domain where energy becomes geometry and geometry becomes information. It is there, in the uncharted realm of quantum gravity, that the dream of controlling gravity might someday find its first glimmer of reality. Gravity is the quiet architect of the universe. It sculpts galaxies from clouds of dust, lights the stars through compression, and shapes the paths of time itself. Yet for all its influence, it remains the most mysterious of nature's forces. We live within its embrace from the moment of birth to the instant our atoms return to the earth, and still we have not learned to speak its language. We have measured it, mapped it, and calculated it with extraordinary precision, but we have never truly understood what it is. To most of us, gravity feels like a downward pull, the invisible hand that keeps our feet pressed to the ground. But this is only how it appears from within our narrow perspective. In truth, gravity is not a thing that pulls, but a condition that guides. It is the shape of space-time itself, a curvature so gentle that we mistake it for force. It is not an arrow pointing down, but a fold in the geometry of reality that makes downward the most natural direction to move. Before we understood this, we treated gravity as a kind of magical glue. It was the link between all material things, a universal attraction that acted across the void. Newton gave this glue a mathematical voice, describing its strength and its reach, but even he admitted he did not know how it worked. The Earth pulled on the Moon, and the Moon pulled on the Earth, without any physical connection between them. There was no cord, no medium, no bridge across the emptiness, only action at a distance, a concept that even Newton found disturbing. He was content to measure what he could and leave the mechanism to future generations. That mechanism turned out to be deeper than anyone could have imagined. Einstein's vision of space-time transformed the mystery from a question of forces to one of geometry. Mass and energy do not send invisible threads across space. They shape the space itself. They bend it, stretch it, and twist it in ways that determine how everything within it must move. When we say that the Moon orbits the Earth, we are really saying that it follows the natural path carved by the Earth's curvature through space-time. The idea seems abstract until we find ways to picture it. The simplest metaphor, though imperfect, is the fabric analogy. The stretched sheet with heavy balls upon it. The deeper the depression in the sheet, the stronger the curvature. Nearby objects roll inward, not because they are pulled, but because their straight paths are curved by the distortion. The universe, on every scale, behaves this way. Planets, stars, and black holes are not surrounded by invisible fields in the classical sense. They are dimples, valleys, and cliffs in the geometry of existence. This shift in perspective changed the way we see not only space, but also time. For in Einstein's theory, the two are not separate realms but aspects of one unified fabric. Where mass curves space, it also affects time. Clocks run more slowly in stronger gravitational fields. This is not a metaphor, but a measurable fact, confirmed countless times by experiment. If you carry a precise clock up a mountain, it will tick a little faster than the same clock left at sea level. The difference is tiny, but it reveals something profound. Gravity does not merely govern motion, it governs the rate at which time itself flows. From this insight arises one of the most extraordinary consequences of relativity. Gravity and acceleration are indistinguishable when observed locally. To an astronaut in a sealed spacecraft, it is impossible to tell whether the pressure they feel on their feet comes from gravity or from the ship accelerating through empty space. This principle, called equivalence, lies at the heart of Einstein's understanding. It means that what we call gravitational force is, in essence, the same as the experience of motion through curved spacetime. But if gravity is geometry, then there is no such thing as a gravitational field in the way we think of electric or magnetic fields. Those can be turned on and off, increased or reversed by changing charges or currents. Gravity offers no such handles. You cannot shield against it, cancel it, or reflect it. Every particle with energy contributes to it, and every other particle responds. It is universal and democratic, treating all matter the same. A feather and a stone fall together not because they are similar, but because gravity does not care about their properties. It cares only about their existence. The beauty of this picture is matched by its strangeness. It tells us that we are not pulled toward the Earth, but are instead following the straightest possible paths through a curved geometry. The word straight here does not mean what it does in Euclidean geometry. It means the path of least resistance, the one that requires no force to follow. When you drop a ball, it simply continues along its natural path, a geodesic, which happens to lead it toward the Earth's center. The curvature of spacetime defines that path, and what we feel as falling is the sensation of being guided by geometry. Einstein's equations capture this relationship with almost poetic simplicity. They state that the curvature of spacetime is determined by the distribution of mass and energy within it. This means that energy and geometry are inseparable. To change one is to change the other. In that sense, gravity is the universe's feedback loop. Mass tells spacetime how to curve, and that curvature tells mass how to move. Once this idea took root, it explained phenomena that had puzzled scientists for generations. The strange orbit of Mercury, which defied Newton's predictions, fell perfectly into place when Einstein's corrections were applied. The bending of starlight near the Sun, confirmed during an eclipse, provided dramatic proof that even light, which has no mass, is guided by curvature, and the slowing of time near massive objects, later measured by atomic clocks, and confirmed in the behavior of satellites, revealed that gravity is not only a spatial phenomenon, but a temporal one as well. The more we studied, the more profound the implications became. Black holes, predicted by Einstein's equations, turned out to be regions where space-time curves so intensely that not even light can escape. They are not merely heavy objects, but boundaries in geometry, where time itself stops from an external perspective. The existence of such entities confirmed that gravity is not just a gentle curvature, but a force capable of tearing the very fabric of reality. This geometric view has changed how we think about motion, mass, and even the meaning of emptiness. What we call empty space is not truly empty, but a dynamic stage that can stretch, twist, and ripple. Those ripples, gravitational waves, are literal vibrations of space-time. When they pass through the Earth, they change distances ever so slightly, stretching and squeezing space by less than the width of an atom. Their detection by instruments such as LIGO proved that space-time is not a static backdrop, but a living medium. And so, the old notion of gravity as a mysterious pull has given way to a deeper understanding. It is not a force in the traditional sense, but a manifestation of geometry, inseparable from the structure of space and time themselves. To control gravity, therefore, is to manipulate geometry, to bend the stage upon which all of existence unfolds. It would be the ultimate act of engineering, requiring mastery not of matter, but of the very coordinates of reality. To approach such mastery, we must understand the cost of curvature, the energy required to warp spacetime even slightly. The universe may reveal its equations freely, but it demands an immense price to act upon them. The next chapter explores that price, showing why the dream of controlling gravity is not a fantasy of imagination, but a challenge of scale, a question of how much energy the universe demands for even the smallest touch upon its fabric. The energy of curvature is one of the most humbling realities in all of physics. Einstein's equations tell us that mass and energy do not simply exist within spacetime, they shape it. Yet when we attempt to grasp how much energy is needed to make even the smallest dent in that structure, we begin to see the scale of the challenge that faces anyone who dreams of controlling gravity. The numbers stretch beyond comprehension, turning ambition into awe. Imagine for a moment that you wanted to create a region of space where gravity is just slightly weaker, perhaps enough to make a person weigh a fraction less than they do on Earth. To do that, you would need to reduce the curvature of spacetime around them. But curvature is not something that changes easily. It is written into the geometry of the universe by the total mass and energy present. To adjust it would require energy comparable to rearranging the mass of the planet itself. The universe bends space effortlessly because it has unimaginable resources at its disposal. Stars, planets, and galaxies contain energy on scales so vast that curvature arises naturally. A single star, burning through nuclear fusion, manipulates spacetime across billions of kilometers without intent or design. The equations of general relativity do not require permission or technology. They are simply the mathematics of existence. Humanity, on the other hand, is a civilization of tiny scales, working with energies that are whispers compared to cosmic roars. Even our most violent experiments, the detonation of a thermonuclear device or the collision of particles at near light speed, barely nudge spacetime, producing curvature too small to measure. The reason for this lies in the way Einstein's equations connect energy and geometry. They are proportional through an enormous constant, one that ensures the universe does not twist and distort wildly with every burst of starlight. This constant acts as a kind of cosmic stabilizer. It means that space-time is incredibly stiff, not in the mechanical sense, but in its resistance to change. The amount of energy required to curve space significantly is so large that it renders direct manipulation impossible with any technology we can imagine today. Consider how gravity behaves across scales. A planet exerts a noticeable pull, but remove a mountain, and the difference is negligible. The gravitational effect of an entire city barely registers. Even the destruction of a massive structure changes the local gravitational field by less than the sensitivity of our best instruments. Gravity, it seems, only becomes dramatic when nature deals in masses like those of stars or black holes. At human scales, it is unyielding and indifferent. And yet, the relationship between energy and curvature remains the key to understanding what gravity truly is. It tells us that every particle, every photon, contributes its own faint influence to the geometry of the universe. When billions upon billions of such contributions combine, the result is the curvature that binds worlds and guides galaxies. This principle, though simple, holds extraordinary implications. It means that if we ever wish to control gravity, we must learn to control energy on a collective level, to orchestrate it across vast regions of space in perfect harmony. Physicists have long explored whether there might be subtler ways to influence curvature without wielding astronomical power. Some have wondered whether certain configurations of electromagnetic fields, plasma, or quantum fluctuations might mimic the effects of mass energy. After all, energy and mass are interchangeable. Perhaps clever arrangements of light or vacuum energy could produce measurable distortions. But every experiment so far has met the same conclusion. The effects are too small, buried beneath the noise of measurement. Space-time resists our touch. This resistance, however, is not absolute. The universe itself bends, stretches, and flexes constantly. Gravitational waves ripple through space as colossal events, black hole mergers or neutron star collisions, send vibrations across billions of light years. When these waves pass through the Earth, they distort everything, expanding and contracting space itself by less than the width of an atomic nucleus. Instruments like LIGO have learned to detect these whispers, proving that space-time can indeed move. That discovery, though far from control, was the first evidence that the geometry of reality can be observed in motion. If observation is the first step, then perhaps manipulation is the second. But how could we ever reach that point? One possibility lies in the quantum realm. General relativity treats space-time as continuous, but quantum mechanics tells us that everything, even energy, comes in discrete packets. Somewhere at the intersection of these two ideas must lie a theory that describes gravity at the smallest scales. If space-time has a granular structure, perhaps we could one day learn to influence those grains. Just as we now manipulate individual atoms, the future may bring technologies that manipulate the quanta of space-time itself. Yet even this possibility carries profound challenges. At such scales, energy and geometry blur into one another, and the difference between space and matter becomes uncertain. Controlling gravity at that level would mean controlling the fundamental information that defines reality. It is not merely an engineering problem, but a philosophical one. Can a system manipulate the geometry that gives rise to its own existence? To bend space intentionally might require stepping outside of it, an ability that may forever remain beyond the reach of beings bound by space-time. Still, the history of science warns against declaring impossibility too soon. The equations we now accept as immutable may one day be tools in a new form. The discovery of how to store and release nuclear energy once seemed unimaginable. The harnessing of electromagnetic fields for communication and computation would have sounded like magic to past centuries. Perhaps one day, with enough understanding, the curvature of space will be another form of energy we can direct. For now, the equations stand as both guide and barrier. They show us the path to controlling gravity, while reminding us how high the price of that control would be. The next question is whether there might exist phenomena, natural or artificial, that can reduce that price. Is there a way to create what physicists call repulsive curvature, an opposite to the attractive geometry we know? Such an effect would not cancel gravity, but reverse its behavior, creating regions where space-time pushes rather than pulls. The search for such effects has driven generations of scientists toward one tantalizing idea: antigravity. If gravity is the geometry of attraction, then antigravity would be its mirror image, a geometry of repulsion. To imagine such a thing is to imagine space itself pushing outward, expanding rather than collapsing. It would mean finding a way to make curvature run in reverse, to turn the valleys of space-time into hills. But is that even possible within the laws we know? The idea of anti-gravity has haunted both science and fiction for more than a century, and its history is one of fascination, frustration, and discovery that always stops just short of revolution. The first to dream of anti-gravity were not physicists, but inventors and storytellers. In the early 20th century, as airplanes took to the skies and science seemed capable of anything, the imagination of humanity turned upward. Writers envisioned ships that floated on invisible fields, machines that rose without wings, and metals that defied the pull of the earth. The idea resonated because it touched a primal hope that gravity, the oldest master of our motion, could one day be tamed. But when science caught up with imagination, it found no easy doorway to that dream. The problem, as general relativity makes clear, is that gravity does not come in opposites. There is no negative mass in nature, no reverse charge of matter that repels instead of attracts. Every form of energy we know contributes to curvature in the same direction. The more energy you add, the more space-time curves inward. To reverse that curvature, you would need a kind of energy that exerts tension rather than pressure. something that pulls outward on the fabric of space. Einstein's equations allow for such a thing in theory, but the universe provides it only on the largest scales, in the form of cosmic expansion. That expansion is driven by what cosmologists call dark energy, a mysterious component of the universe that makes up most of its total energy. Dark energy acts as a kind of negative pressure, pushing space apart rather than pulling it together. It is, in a sense, the only known example of repulsive gravity. Yet its power is subtle, spread evenly across the cosmos, and its effect is gentle on small scales. It accelerates the universe's expansion, but cannot lift a single pebble from the ground. To harness it, we would need to concentrate it, to shape it, to build with it, and that, as far as we can tell, is far beyond our reach. Still, humans have tried to imitate nature's repulsion. In the late 20th century, experiments began that sought to manipulate gravity directly through technology. One of the most famous came from a Russian researcher named Eugene Podkletnov, who claimed that a spinning superconducting disk could slightly reduce the weight of objects above it. The effect, he said, was small but measurable, a few % decrease in gravitational pull. The announcement caused a sensation. If true, it would have been the first real evidence of gravity being altered by human means. But science demands more than claims. It demands repetition and verification. When other researchers tried to reproduce the experiment, they found nothing. No weight reduction, no measurable anomaly, nothing that defied known physics. The scientific community concluded that Podkletnov's result was likely an artifact of experimental error or measurement interference. Despite this, the allure of his claim lingered, inspiring decades of speculation about whether superconductors or magnetic fields might somehow couple to gravity. So far, the answer remains no. Around the same time, agencies like NASA explored the limits of what was then called breakthrough propulsion physics. The idea was to examine every unconventional theory that might hint at new forms of propulsion, including antigravity, warp drives, and field manipulation. The program attracted attention but produced no tangible success. Every proposed mechanism either violated known laws or required energy levels beyond what technology could provide. When funding ended, so did the official search. But the dream survived in labs and minds around the world. Physicists, who approached the question with skepticism, still found value in the pursuit. Testing the limits of gravity often led to deeper understanding of its subtleties. Theories about vacuum energy, quantum fluctuations, and the possible relationship between gravity and the quantum world began to take shape. Each attempt to find a loophole revealed new insights into why gravity behaves as it does. It became clear that any genuine control over it would require a revolution, not in technology, but in theory. Modern physics tells us that the only known way to produce repulsive curvature is through energy with negative pressure, something that acts as if it has less than zero gravitational mass. This is what drives the expansion of the universe, what keeps galaxies moving apart faster over time. It is not an exotic invention, but a natural feature of the cosmos, one we still barely understand. If we could somehow isolate and manipulate that property, we might have the foundation for true antigravity. But the density of dark energy is extraordinarily low, a whisper spread through infinite space. To gather enough of it to lift even a feather would require a region larger than a galaxy. The irony is that while we cannot yet create repulsive gravity, the universe does it effortlessly. It expands without engines, accelerates without fuel, and bends its own fabric with invisible precision. Perhaps what we call dark energy is not a substance at all, but a property of spacetime itself, a reminder that the universe does not need permission to evolve. We, on the other hand, are confined within its geometry, still learning to measure the smallest of its movements. Antigravity, as a concept, remains a phantom, not disproven, but unproven. Every experiment, every theoretical framework comes back to the same truth. Gravity is not something we can shield or oppose in the traditional sense. To control it, we must understand it at a level far deeper than mass and energy. We must explore the quantum foundation of spacetime, the realm where geometry may arise from something even more fundamental. The search for antigravity thus becomes the search for the quantum origin of gravity itself. If spacetime is not a continuous fabric, but an emergent structure born from information, then perhaps gravity is not truly a fundamental force, but a byproduct, a kind of illusion created by the interactions of countless quantum states. If that is true, then the control of gravity might someday come not from bending space with mass, but from manipulating the information that defines space in the first place. The dream of anti-gravity, then, is not dead. It is evolving. It points us toward the next great mystery, how the quantum and the cosmic, the smallest and the largest, might be bound together by rules we have only begun to glimpse. To reach that frontier, we must follow the thread of thought from Einstein's geometry down into the quantum sea, where the very fabric of spacetime trembles with uncertainty. There, in the world of probabilities and entanglement, the next chapter of gravity's story begins. Gravity is not a force in the ordinary sense. It is the shape of existence itself. Einstein's equations describe that shape in the language of geometry, linking the curvature of spacetime to the energy and momentum within it. In symbolic form, those equations tell us that geometry equals energy. Every curve in the fabric of reality corresponds to the presence of mass, light, or pressure. This relationship is so perfect that by measuring one, we can predict the other. Yet hidden in that beauty is a vast gulf between what nature achieves effortlessly and what humanity could ever hope to imitate. The energy required to warp spacetime is almost beyond imagination. To curve space even slightly across the span of a single room would demand the energy of an entire planet. To twist it enough to noticeably change gravity's pull would take the output of a star. The numbers are so immense that they lose meaning. We speak of 10s to the power of 45 joules, a quantity so large that even the total energy humanity has ever generated does not begin to register against it. And yet, the universe performs such feats without hesitation. Black holes, neutron stars, and the dense cores of galaxies bend spacetime into wild geometries, turning straight lines into spirals and time into a slow crawl. These structures show us that gravity is not a passive feature of the cosmos, but a dynamic expression of energy at its most concentrated. The universe bends, folds, and stretches itself because it contains the power to do so. If humanity ever hopes to control gravity, we must learn how to manipulate energy with the same effortless precision. Consider what this means in practice. When a star forms, immense clouds of gas collapse under their own weight, converting gravitational potential energy into heat and light. That process continues until the star stabilizes, its outward pressure balancing its inward pull. The star does not fight gravity, it dances with it. The curvature of spacetime guides the movement of the gas, while the energy released by nuclear fusion pushes back against that curvature. This balance is nature's most delicate act, a dialogue between energy and geometry so exact that it can last billions of years. We can see similar balances on smaller scales. A planet like Earth shapes spacetime just enough to hold its atmosphere and keep the moon in orbit. A galaxy, with its billions of stars, bends spacetime on scales of hundreds of thousands of light years, creating a gravitational lens that magnifies distant light. Everywhere we look, the pattern holds true. Energy curves space, and that curvature defines how energy moves. This feedback loop lies at the heart of Einstein's field equations. They tell us that matter tells spacetime how to curve, and spacetime tells matter how to move. But it also tells us something else, that gravity is a kind of conversation between energy and geometry that never stops. Every fluctuation, every photon, every wisp of radiation contributes its own whisper to the cosmic dialogue. To imagine controlling gravity, then, is to imagine interrupting or rewriting that dialogue. It would mean injecting energy into space-time in a way that changes how the universe balances itself. We already do this in tiny, indirect ways. When a spacecraft launches, it redistributes mass and momentum, subtly altering the Earth's curvature. When light bounces between mirrors in a laboratory, it adds the tiniest tremor to the geometry around it. But these effects are microscopic, so faint that they vanish into the background hum of spacetime's natural vibration. If we could somehow amplify such effects, we might begin to see the outlines of gravitational engineering. The difficulty is that energy itself gravitates. Any energy you add to try to bend spacetime also adds to the total curvature you are trying to control. It is a self-reinforcing loop that resists manipulation. The more power you apply, the more gravity you create. The trick, if it exists, would be to find a kind of energy that curves spacetime in the opposite direction, something that exerts tension rather than pressure. The concept of negative energy emerges here, not as science fiction, but as a mathematical curiosity. According to general relativity, certain forms of energy could, in theory, produce repulsive curvature. Such energy would make space expand locally rather than contract. But every attempt to find or create it has failed. Quantum field theory predicts that the vacuum of space itself fluctuates with energy, yet these fluctuations average out to zero at scales we can measure. If negative energy exists, it hides within the quantum foam, beyond our instruments. The connection between energy and curvature is not merely abstract. It shapes the very passage of time. Near massive objects, where energy density is high, space-time curves sharply, and time slows relative to regions of weaker gravity. This is not perception, it is reality. The clocks aboard satellites orbiting the Earth tick faster than those on the ground because they reside in a slightly weaker gravitational potential. Engineers must correct for this difference to keep the global positioning system accurate. The lesson is profound. Controlling gravity would also mean controlling time itself. Every attempt to visualize these relationships reveals the same truth. Gravity is geometry written in energy. Imagine a rubber sheet stretched across a frame. Place a heavy sphere on it, and the sheet curves downward. Now imagine trying to lift that curve back to flatness without touching the sphere. You would have to pull upward on the sheet with immense force from all directions at once. That force is the equivalent of the energy required to oppose gravity. The heavier the sphere, the deeper the curve, and the greater the energy you would need. Even light contributes to this curvature. Though it has no rest mass, its energy and momentum bend spacetime ever so slightly. A beam of intense laser light produces a gravitational field, but the effect is so weak that it can only be detected in theory. The curvature caused by a laser powerful enough to vaporize steel would still be smaller than 1/1,000,000,000 of 1/1,000,000,000,000 the curvature created by the Earth. Spacetime, for all its fluid imagery, is astonishingly rigid. This rigidity has profound consequences for the future of science. It means that gravity will not yield to us through simple machines or incremental progress. To control it, we must either command energies comparable to celestial bodies or uncover new principles that allow us to mimic those effects indirectly. Perhaps the answer lies not in brute force, but in subtlety, in finding ways to shape geometry through the collective behavior of particles or fields at the quantum level. The realization that energy and curvature are two sides of the same coin leads naturally to the next question. If energy can bend space, can information? Some modern theories suggest that gravity itself may emerge from the structure of quantum information, from the way particles become entangled and share their states across space. If that is true, then curvature might not be a fundamental property at all, but a statistical outcome of deeper connections. In that case, learning to control gravity might one day mean learning to control information itself. The path forward, then, is not simply about generating more energy. It is about understanding how energy, information, and geometry intertwine. The next step on this journey lies at the edge of what we know, the domain of quantum gravity, where the smooth fabric of space-time dissolves into a sea of probabilities, and where the curvature of reality may arise from patterns we have only begun to glimpse. At the edge of ordinary experience, gravity behaves in ways that are calm and predictable. It holds the oceans in place, guides the moon through its orbit, and makes apples fall as they always have. But far from the safety of human scale, in the hearts of stars or the throats of black holes, gravity becomes an artist of extremes. Here, space-time twists and folds upon itself with ferocity, revealing how deeply it depends on energy. The connection between curvature and energy density becomes undeniable. Every rise in mass, every surge in temperature or pressure, reshapes geometry in ways that the human mind struggles to visualize. In these places, the equations of general relativity are both our guide and our limit. They tell us exactly what should happen, but they also tell us when they can no longer be trusted. At densities too high, the fabric of space-time curves so tightly that the mathematics breaks down. Inside a black hole, for example, the curvature becomes infinite, a singularity. At that point, our equations lose meaning. It is as though the language of the universe collapses into silence. Somewhere beyond that silence must lie a deeper description, one that unites Einstein's smooth geometry with the restless quantum world that governs the small. The relationship between energy and curvature becomes most dramatic in these extremes. A black hole is not simply an object of enormous mass. It is a region where energy density has crushed space and time together. The boundary around it, called the event horizon, marks the place where escape becomes impossible. It is not a physical surface, but a point of no return, a region of space-time so curved that every possible path leads inward. Time slows near this boundary, nearly freezing from an outside perspective. For an observer at a safe distance, the fall into a black hole never quite finishes. The object appears to hover forever, dimming into red oblivion. These extremes illustrate the raw power of energy as the sculptor of space-time. The more concentrated the energy, the steeper the curve. But even at such scales, energy follows rules. It can neither be created nor destroyed, only transformed. Gravity respects this balance. When a massive star collapses under its own weight, it converts potential energy into curvature, creating the intense geometry we call a black hole. The process is not mystical. It is the ultimate expression of the same principle that makes an apple fall. Energy shapes space, and space guides energy. For physicists, this interplay raises profound questions. If gravity is curvature, and curvature is energy, then where does one truly end and the other begin? The boundary between geometry and matter may not exist at all. Some researchers propose that space-time itself is a manifestation of energy, that what we perceive as geometry emerges from deeper quantum fields. Others go further, suggesting that energy and information are two expressions of the same substance, and that gravity may simply be the statistical behavior of vast networks of quantum information. These ideas are not yet proven, but they carry an important message. They suggest that the path to controlling gravity does not lie in brute strength. It lies in understanding the code from which gravity emerges. If curvature is a byproduct of quantum relationships, then perhaps by mastering those relationships, we could influence curvature without enormous energy. This is speculation, but it echoes a pattern seen throughout science. Each time we learn to look deeper, the impossible becomes manageable. Think of how humans once faced electricity. Before the 19th century, lightning was a terrifying mystery. Only when we learned that it was a natural expression of charge did it become something we could harness. The same may one day be true of gravity. The challenge is that gravity does not reveal itself in sparks or flashes. It hides in the equations of space-time, in relationships too subtle for the senses. We cannot see curvature, but we can see its consequences. When a beam of starlight bends around the sun, when the orbit of a planet shifts by a fraction, when a clock runs slower on a mountain, these are the fingerprints of geometry. Even at these gentle scales, the interplay of energy and curvature shapes every aspect of existence. The expansion of the universe itself is a grand expression of energy acting on geometry. The mysterious force we call dark energy behaves like an invisible pressure that stretches space faster with time. It is a reminder that curvature is not always about attraction. Sometimes it repels. Though we cannot yet control such cosmic behavior, studying it reveals that the universe already performs the feats we dream of achieving. The lesson of these observations is that gravity, though universal, is not uniform. It can vary, shift, and even reverse direction under the right conditions. This variability proves that curvature can change, and if it can change, then in principle it can be engineered. The problem is scale. Nature performs its experiments with entire galaxies. We must work with laboratories no larger than cities. To bridge that gap requires not just technology, but insight, a way to translate the mathematics of curvature into the language of materials and fields. For decades, physicists have searched for hints of how this might be done. Some have explored the behavior of superfluids, plasma, or high-energy magnetic fields, wondering whether they can mimic gravitational effects in miniature. Others have used quantum simulations, mapping the mathematics of spacetime onto systems of atoms and photons. These efforts do not bend space directly, but they let us observe its analogues, small-scale imitations of curvature, where the laws can be tested safely. In doing so, they bring us a step closer to understanding what it would mean to shape gravity. At the heart of these explorations lies a deeper truth about the universe. Gravity does not resist us out of hostility. It resists because it is woven into everything. To manipulate it, we must engage with the totality of existence, not a separate force, but the stage on which all forces act. It is the background that becomes the foreground the moment we try to change it. Every step toward understanding gravity is also a step toward understanding the nature of reality itself. To reach the next stage of that understanding, we must turn to the scale where geometry and quantum behavior meet, the microscopic realm where space-time begins to shimmer with uncertainty. It is here that the smooth fabric of Einstein's universe dissolves into something more granular, where gravity may arise not from mass or energy alone, but from the entanglement of countless invisible threads of information. This is the realm of quantum gravity, the frontier where the laws of the large and the small finally converge. The search for the connection between energy and curvature leads inevitably into the smallest scales of existence, where space-time ceases to behave as a smooth fabric and begins to flicker like a restless sea. Here, distances lose their fixed meaning, and the geometry that seems continuous at human scale breaks into uncertainty. It is a realm ruled not by certainty but by probability, where particles exist as waves of possibility and energy fluctuates endlessly in the vacuum. This is the quantum world, and it is here that the true mystery of gravity deepens. Einstein's equations describe how energy shapes space-time, but they assume that space-time itself is continuous. Quantum mechanics, on the other hand, insists that everything comes in discrete packets, quanta. If both theories are right, then space and time must also have a quantum structure made of fundamental units that we have not yet identified. The problem is that the two theories speak different languages. Relativity describes smooth curves and continuous flows. Quantum theory describes jumps, uncertainties, and probabilities. Each is complete within its own domain. But when we try to use them together, the mathematics shatters. This conflict is not a flaw of science, but a sign that we stand at the edge of what we know. It tells us that our understanding of energy and curvature is incomplete. If gravity emerges from geometry, and geometry itself may emerge from something deeper, then we are missing the bridge between these levels of reality. That bridge is what physicists call quantum gravity, the theory that would unify the laws of the very large and the very small. Quantum gravity remains one of the greatest unsolved problems in physics. Many paths have been proposed. Some imagine spacetime as a web of tiny loops, like threads woven together at the Planck scale, where each loop represents a quantum of area. This approach, known as loop quantum gravity, suggests that the smooth curvature of Einstein's equations is just the large-scale average of these microscopic loops. Others turn to string theory, where the fundamental ingredients of the universe are not points or loops of space, but vibrating strings of energy. In this view, gravity emerges naturally from one of the string's vibrational modes, a particle called the graviton. The graviton is the hypothetical quantum carrier of gravity, the equivalent of the photon for electromagnetism. If it exists, it would be a particle that mediates the curvature of spacetime itself. Detecting such a particle would confirm that gravity, too, can be quantized, that it follows the same discrete logic as all other forces. But the graviton is elusive beyond measure. Because gravity is so weak compared to the other fundamental interactions, a single graviton would be drowned in noise long before we could ever detect it. Even the most ambitious experiments struggle against limits set by the universe itself. Despite this, the pursuit of quantum gravity continues, because it may hold the key to controlling curvature in ways we cannot yet imagine. If gravity arises from the collective behavior of quantum systems, then influencing those systems could, in principle, influence gravity. Some physicists even speculate that spacetime might emerge from quantum entanglement, the invisible connection that allows particles to share information instantly across distance. If true, this would mean that gravity is not a fundamental force at all, but an emergent property of information itself. Such an idea seems abstract, but it carries practical implications. If geometry arises from information, then perhaps manipulating information could change geometry. It would be a new kind of engineering, not mechanical, but informational. Instead of building machines that push against matter, we might someday design systems that rearrange the informational structure of space. This is far beyond our current reach, but it points to a future where the control of gravity might come not from energy, but from understanding how the universe encodes itself. In the meantime, the best evidence of the link between quantum behavior and curvature comes from extreme conditions where both effects are strong. Near black holes, the energy of curvature becomes so concentrated that quantum effects can no longer be ignored. According to Stephen Hawking's calculations, the boundary of a black hole is not entirely silent. Quantum fluctuations near the event horizon allow pairs of particles to appear from the vacuum, one falling in, while the other escapes as radiation. This process slowly reduces the mass of the black hole, proving that even the most extreme curvature interacts with the quantum world. This discovery reshaped how physicists view spacetime. It showed that the vacuum is not empty, but alive with energy. Space itself has structure, woven from fluctuations that constantly appear and vanish. Those fluctuations generate tiny, momentary curvatures, ripples in the geometry that balance each other out on average. If we could ever learn to bias that balance, to favor one kind of fluctuation over another, we might begin to produce controlled distortions of spacetime. The effect would be unimaginably small at first, but conceptually it would mark the first true manipulation of gravity at the quantum level. The idea of vacuum energy connects to another mystery, the cosmological constant, the term in Einstein's equations that represents the energy density of empty space. For decades, it was considered negligible, but modern cosmology shows that it drives the acceleration of the universe's expansion. The vacuum itself, it turns out, carries energy that curves space outward, creating repulsive gravity on a cosmic scale. This means that even nothingness has weight, and that the geometry of the universe depends as much on the quantum fabric of emptiness as on the matter it contains. The challenge, then, is scale. At the quantum level, fluctuations are immense but fleeting, cancelling each other almost instantly. On cosmic scales, they average out into the gentle push of dark energy. Somewhere between those two extremes lies the realm where control might become possible. If we could learn to manipulate the quantum structure of space locally, to amplify certain fluctuations or suppress others, we might bend geometry without enormous mass or energy. Such a breakthrough would turn the dream of gravitational control into a matter of precision rather than power. For now, this remains speculation. We do not yet possess a full theory of quantum gravity, nor the technology to probe spacetime at the Planck scale, but the path is clear. The more we learn about how energy, information, and geometry intertwine, the closer we come to understanding gravity not as a force to overcome, but as a field to be shaped. The energy of curvature, once thought unreachable, may one day be guided by thought and design, the same way electricity and magnetism once were. If that day comes, it will not be the conquest of gravity, but its partnership. We will not defeat the geometry of the universe. We will learn to work within it, to write new patterns into the cosmic fabric. The first step toward that future is not found in laboratories or engines, but in understanding, in seeing that gravity, energy, and information are three expressions of the same underlying reality. To master one is to touch the others. The quest to control gravity, therefore, is not merely technological, it is philosophical. It challenges us to ask what space and time truly are, and whether reality itself might be more flexible than we ever believed. The universe bends easily for those who understand its shape. The question is whether humanity will ever learn the language well enough to speak it. The dream of anti-gravity has always lived at the border between physics and imagination. It is the vision of a universe where gravity, the most ancient and universal of forces, could be turned down, reversed, or even switched off entirely. It is the promise of flight without fuel, of ships that rise silently into the sky, of worlds unbound by their own weight. Yet every time science has chased that dream, it has found not freedom but deeper mystery. Gravity has yielded its secrets reluctantly, never surrendering its hold on reality. To understand why, we must begin with what anti-gravity truly means. In the language of physics, anti-gravity is not the absence of gravity, but the creation of curvature that pushes rather than pulls. Ordinary gravity arises from positive energy density, mass and energy that curves space-time inward. Anti-gravity would require negative energy density, the kind of exotic condition that makes space expand instead of contract. We have seen such behavior only once in nature, and it is not on any planet or laboratory table. It is written into the universe itself. When astronomers discovered that distant galaxies were not slowing down but accelerating away from one another, they realized that the cosmos is filled with a strange form of energy, dark energy, that acts as a repulsive gravity. It pushes the universe outward, making space expand faster over time. It is not a force in the traditional sense, but a property of space-time, a pressure that cannot be turned off. It is the only known form of anti-gravity that actually exists, and it operates everywhere, invisibly, at every moment. But its power is spread so thinly that its effect is felt only across billions of light years. Within a laboratory, its influence is too faint to measure. Still, the idea of artificial anti-gravity continues to fascinate scientists and inventors alike. Throughout the 20th century, there were claims of devices that could cancel or shield gravity. None have survived scrutiny. The problem is that gravity, unlike electromagnetism, has no polarity to exploit. There is no negative mass to counteract positive mass, no north and south pole of attraction. It pulls universally on everything with energy. Shielding gravity would require a material that does not interact with the geometry of space-time, something that lies outside existence itself. One of the most famous modern claims came in the 1990s from a researcher named Eugene Podkletnov. Working with superconductors, he reported that objects suspended above a spinning disk lost a small fraction of their weight. The effect, if real, would have been revolutionary. Scientists rushed to replicate the experiment, but no one could reproduce the result. Every attempt produced normal gravitational behavior. The original claim, it seemed, had been a measurement error or a misunderstanding of the equipment. The dream of a gravity shield faded again into the background, filed away among other curious but unverified anomalies. NASA's Breakthrough Propulsion Physics program, launched in the late 1990s, approached the question with caution and scientific discipline. It gathered proposals from across the world: warp drives, reactionless thrusters, gravity manipulators, and subjected them to careful analysis. Each idea failed the same test. It required energies or conditions beyond reach, or violated fundamental conservation laws. When the program ended, it left behind not blueprints, but clarity. There were no known ways to cancel or reverse gravity, yet the effort had not been wasted. Every failure deepened our understanding of why gravity behaves the way it does. Physicists now define antigravity in precise terms. It is any condition where spacetime curvature acts repulsively rather than attractively. The only known natural example is dark energy, which causes the expansion of the universe. In Einstein's equations, this corresponds to a form of energy with negative pressure, something that pushes outward on space itself. It does not require exotic matter with negative mass. It arises simply from the vacuum of quantum fields. But the density of that vacuum energy is astonishingly small. Even if we could gather and amplify it, the effect on human scales would be negligible. To produce the same repulsion that the cosmos experiences would require harnessing the energy of countless stars, focused within a region smaller than an atom. This sobering reality explains why so many laboratory efforts fail. They attempt to create curvature changes with electromagnetic or mechanical systems that manipulate only local fields. Gravity does not respond to such tinkering because it is not a separate force to be redirected. It is the geometry of all existence. To alter it meaningfully, we must work at the level of space-time itself. That is a level of control that even the universe achieves only through its largest structures. And yet, hope persists, not in the promise of machines that defy physics, but in the realization that the laws themselves might hold possibilities still unseen. Einstein's equations allow for many kinds of curvature, some of which behave like anti-gravity in limited regions. One example is the theoretical wormhole, a tunnel through space-time that connects distant points. For such a structure to remain open, it would require negative energy to counteract the inward pull of gravity. Though no one knows whether such energy can exist in stable form, its mathematical presence proves that the universe's geometry allows it in principle. Another example is the Alcubierre warp drive, a theoretical solution proposed in the 1990s. It describes a bubble of space-time that contracts in front of a spacecraft and expands behind it, allowing faster-than-light travel without breaking relativity. The catch, once again, is energy. To create such a bubble, one would need negative energy density, precisely the kind of curvature reversal that anti-gravity demands. No known form of matter or field can produce it. Yet the mathematics works, which means the idea cannot be dismissed entirely. It stands as a reminder that the boundary between impossible and undiscovered is often thin. Real progress, however, depends on evidence. Scientists continue to test gravity with exquisite precision, searching for any deviation from Einstein's predictions. So far, gravity behaves exactly as expected. No shielding, no repulsion, no anomalies. But that precision itself is an achievement. It tells us that if new physics exists, it hides at scales we have not yet reached. The path to anti-gravity may not lie in rejecting relativity, but in extending it into the quantum domain, where the geometry of space-time might be more malleable than it seems. Even as science rules out false claims, the pursuit of anti-gravity has value. It forces us to ask deeper questions about the nature of space, energy, and motion. Why can every other fundamental force be both attractive and repulsive, while gravity only attracts? Why does mass always curve space-time in one direction? These questions lead directly into the search for a unified theory, the framework that could explain not only gravity's behavior, but its origin. For now, gravity remains indifferent to our efforts. It continues to pull relentlessly, patient and absolute. But each failure teaches us something. The experiments with superconductors revealed that the link between electromagnetism and gravity, if it exists, is unimaginably subtle. The studies of cosmic expansion revealed that repulsive curvature does exist, though far beyond our ability to command. Together, these lessons point to a single conclusion. Gravity can be influenced, but not yet controlled. The story of anti-gravity, then, is not one of defeat, but of refinement. It has stripped away illusions and forced physics to confront the true complexity of space-time. It has revealed that to change gravity, we must work with the universe's most fundamental ingredients: energy, information, and geometry, not against them. It is not a matter of inventing a new machine, but of discovering a new level of understanding. The next step on this journey leads us even deeper, to the frontier where Einstein's smooth geometry meets the uncertainty of quantum mechanics. If gravity cannot be conquered by magnets or engines, perhaps it can be understood and eventually shaped through the laws that govern the smallest scales of existence. In that realm, where particles and probabilities intertwine, the first glimpses of true gravitational control might one day appear. Anti-gravity, despite its name, has never been about escaping the laws of physics. It has always been about expanding them, asking whether the universe allows for new forms of motion, new relationships between energy and curvature that we have not yet discovered. After the early decades of failed experiments, the scientific search for anti-gravity shifted from mechanical speculation to fundamental theory. The focus moved from spinning disks and magnetic tricks to the quantum world, where gravity might reveal a softer, more malleable side. In the 21st century, this pursuit found a new shape. Physicists began asking whether space-time itself could be manipulated indirectly, not through massive objects, but through the vacuum, the quantum field that fills all space. The vacuum is not empty. It seethes with particles that appear and vanish in pairs, their energies balancing perfectly, so that the total remains almost zero. These fluctuations are real and measurable, as shown in phenomena like the Casimir effect, where two metal plates placed close together experience a faint attraction caused by changes in the vacuum energy between them. That tiny force, a product of quantum geometry, hints that space-time can indeed respond to the arrangement of matter and energy at microscopic scales. If the vacuum can exert such influence, could it be coaxed to push instead of pull? The idea led to a line of research exploring negative energy states, configurations where the energy density of the vacuum drops below its normal level. In principle, such states could generate repulsive curvature, a localized form of anti-gravity. Quantum field theory does not forbid negative energy. It allows it briefly within the limits of the uncertainty principle. The challenge is duration and scale. Negative energy can exist, but only fleetingly, and only in amounts so small that they average out almost instantly. Holding such a state stable enough to affect space-time would require technology far beyond anything we possess. Nevertheless, theoretical work continued. Researchers examined whether strong electromagnetic fields, superconductors, or high-intensity lasers could influence gravity indirectly by altering the energy of the vacuum. The results so far are consistent. Space-time does not react to these manipulations in any measurable way. The gravitational effects, if they exist, are smaller than 1 part in 10 to the power of 30, yet even the search itself has value. Each experiment refines our understanding of how energy and curvature interact. tightening the boundaries of what is possible and revealing where the unknown still hides. One of the most intriguing directions emerged from the study of dark energy. If the universe's acceleration is caused by the vacuum energy of space, then anti-gravity is not a fantasy, but a fundamental feature of reality, just one we cannot localize. The key might be scale. On cosmological distances, dark energy dominates because matter becomes sparse. On small scales, the effects of mass overwhelm it. If a way could be found to alter that balance, to change the local ratio of vacuum energy to mass energy, then space-time itself might respond. Some speculative models suggest that even a slight modification of vacuum energy density could produce measurable curvature, provided it could be controlled with precision. The difficulty, of course, is that vacuum energy is enormous but hidden. Quantum theory predicts that the energy density of empty space should be immense, 120 orders of magnitude greater than what we observe. Yet for reasons still unknown, almost all of it cancels out. What remains is the faint residue we call dark energy. This enormous mismatch, known as the cosmological constant problem, is one of the greatest puzzles in science. It implies that the universe already fine-tunes its own vacuum energy to a near-perfect balance. If we could understand that mechanism, perhaps we could learn to adjust it, to tip the scales slightly in one direction or another. While these ideas remain far beyond experiment, the boundary between theoretical and practical exploration is slowly shifting. New instruments, such as atom interferometers, are measuring gravitational effects at microscopic scales with unprecedented sensitivity. These experiments use clouds of ultra-cold atoms to detect minute changes in gravitational potential. They have already verified Einstein's predictions to remarkable accuracy. In the future, they may reveal tiny deviations that point toward new physics, hints of how gravity behaves in the transition between classical and quantum realms. Some researchers have proposed that certain configurations of electromagnetic energy might mimic gravitational fields through what they call induced curvature. In these models, intense fields could slightly distort space-time geometry, though the effect would be so faint as to be nearly undetectable. Others investigate whether the motion of superfluid helium or Bose-Einstein condensates can simulate gravitational behavior. These materials exhibit quantum coherence on a macroscopic scale, behaving as single quantum entities. Under the right conditions, they can reproduce aspects of space-time curvature, allowing scientists to study gravitational analogues in the laboratory. Such analogues are not true gravity control, but they are powerful tools. They let physicists test ideas about horizons, waves, and curvature in controlled environments. When researchers create sonic black holes, regions where sound cannot escape, they are effectively building laboratory models of space-time geometry. In these miniature analogues, information, energy, and curvature interact just as they would near an astrophysical black hole. Each result teaches us something new about how gravity behaves and how it might, one day, be influenced. Even as these investigations progress, the notion of anti-gravity continues to evolve. The most serious scientists no longer chase the idea of weightless engines or gravity shields. They seek instead to understand what gravity really is and whether it can emerge from something deeper. In this sense, the quest for anti-gravity has transformed into the search for quantum gravity itself. What began as a technological dream has become a philosophical and scientific challenge to comprehend how the universe writes its own geometry and whether that script can ever be rewritten. For now, gravity remains the one fundamental interaction that resists control. We can channel electricity, direct magnetism, and even split the atom, but we cannot yet command curvature. Still, the history of physics offers a lesson worth remembering. Every impossibility is temporary. Each frontier that once seemed absolute has eventually fallen to understanding. The laws of the universe are not chains, they are invitations. To dream of anti-gravity is to accept that invitation. to look at the unyielding pull beneath our feet and see not a prison, but a puzzle waiting to be solved. The next step in that puzzle takes us further into the unknown, toward the quantum realm where gravity and geometry might be born from the same hidden code. If gravity can emerge from the entanglement of particles and the structure of information itself, then the key to controlling it may lie not in matter or motion, but in the logic of the universe's own design. To explore that possibility is to enter the frontier of quantum gravity, where the energy of curvature meets the smallest scales of reality, and where science begins to glimpse the architecture of existence itself. The search for anti-gravity has become less a hunt for miracle devices, and more an effort to understand how far the laws of nature can bend before they break. What once belonged to science fiction now serves as a probe into the foundations of physics itself. The goal is no longer to build a machine that floats effortlessly above the Earth, but to find the principles that explain why gravity always attracts, why it never turns against itself, and whether the geometry of spacetime might hold hidden degrees of freedom we have yet to see. In the last few decades, physicists have examined every possible clue. Some have revisited the nature of mass itself, asking whether what we call gravitational mass and inertial mass, the two quantities that Einstein proved to be identical, might someday diverge under extreme conditions. If they did, even slightly, it could hint at a mechanism for manipulating weight without directly altering curvature. Precision experiments using atom interferometers, torsion balances, and cold neutron beams have searched for such deviations. So far, the equivalence remains perfect within the limits of measurement. No difference has ever been found. Others have explored the idea that exotic forms of matter could alter gravity's behavior. In theoretical cosmology, exotic matter refers to any substance with properties unlike those of ordinary atoms. For example, matter with negative pressure or energy density. Such material would bend spacetime in the opposite direction, creating repulsive curvature. The equations of relativity allow this in principle, but no known process in nature produces it in a stable form. Even quantum field theory, generous as it is with strange predictions, does not provide a recipe for negative energy that can persist longer than a fleeting instant. Despite that, some researchers continue to look for hints that exotic matter might exist. Observations of cosmic acceleration, dark energy, and high-energy astrophysical events all suggest that the universe is stranger than we expected. In the cores of neutron stars or in the earliest moments after the Big Bang, conditions may have existed where the normal relationship between pressure and energy reversed, producing temporary regions of repulsive curvature. These moments, though fleeting, might hold the key to understanding whether such states can exist elsewhere. If they can, then anti-gravity is not a fantasy. It is simply a phenomenon awaiting the right conditions. Gravitational shielding, another idea once popular in speculative physics, has not survived experimental scrutiny. The notion was simple. If gravity behaves like a field, perhaps a material could block or absorb it. But gravity does not travel through space like light or magnetism. It is the structure of space itself. No material can isolate one region of spacetime from another. Experiments from the early 20th century to the present have searched for shielding effects by weighing objects during solar eclipses, by measuring gravitational pull through different materials, and by rotating superconductors in magnetic fields. In every case, gravity passed through unimpeded. The results confirmed Einstein's insight. Gravity is universal, unscreenable, and absolute. Yet this very universality may hide deeper truths. Some physicists suspect that gravity's weakness compared to other forces hints at extra dimensions beyond our perception. If space-time extends beyond the familiar 3 dimensions of space and one of time, then gravity might leak into those hidden dimensions, explaining why it seems so faint in ours. In such theories, controlling gravity might one day mean learning to influence how it propagates through the higher dimensional structure. While these models remain speculative, they have inspired new generations of experiments using particle accelerators and precision cosmology to search for signs of extra-dimensional curvature. The pursuit of anti-gravity has thus evolved into a broad exploration of what spacetime can do. It no longer belongs solely to dreamers, but to careful experimenters, testing the limits of Einstein's theory. Each test, from the falling of atoms in vacuum chambers to the detection of gravitational waves, confirms how deeply gravity is woven into reality. It refuses shortcuts, but rewards persistence. The more precisely we measure it, the more we glimpse its subtleties. For instance, the detection of gravitational waves in 2015 proved that spacetime is not static, but dynamic. Massive bodies moving through it create ripples that travel across the cosmos, carrying energy in pure curvature. These waves confirmed one of Einstein's final predictions and opened a new way to observe the universe. They also offered a tantalizing clue. If we can detect spacetime's vibrations, perhaps one day we can generate them. Learning to produce controlled gravitational waves, however weak, would be the first real act of engineering curvature. Another line of study investigates how gravity behaves at the quantum level, where its smoothness begins to blur. If spacetime has a granular structure, as loop quantum gravity suggests, then it might respond to energy in quantized steps rather than continuous curves. That could mean there are natural thresholds, small windows where the geometry becomes more flexible. Understanding those thresholds might someday allow manipulation of curvature without astronomical energy. The challenge is that we cannot yet reach or measure the Planck scale where such effects become visible. For now, the closest humanity has come to altering gravity is through motion and acceleration, the old, faithful methods that rely on the equivalence principle. Rotating habitats in space can simulate gravity through centrifugal force. Accelerating spacecraft can mimic weight for their crews. These methods do not control gravity, they imitate it. But they remind us that gravity and acceleration are two sides of the same experience. To create one may be to influence the other. If we can ever produce acceleration by shaping spacetime rather than pushing against it, the line between imitation and control will finally blur. In every sense, anti-gravity remains a frontier rather than a fantasy. It is not forbidden by the laws of nature, only hidden by their complexity. Each experiment that fails to find it narrows the search and sharpens the question. Perhaps gravity cannot be neutralized, but it can be redirected. Perhaps we cannot cancel its pull, but we can bend its direction. These possibilities, subtle and profound, are the seeds of future exploration. To move forward, science must turn inward, toward the quantum foundations of reality, where space and time themselves may be emergent. The next step in understanding gravity is not to resist it, but to comprehend its source. If the fabric of space-time arises from the collective behavior of quantum entities, then mastering gravity will mean mastering that collective, learning to write the rules of geometry from the smallest building blocks of the cosmos. The dream of anti-gravity has taken us from spinning disks to the edge of quantum theory. It has shown that the true path to control lies not in defiance, but in understanding. The next chapter begins at the frontier where quantum mechanics and general relativity meet, the search for a single theory that unites them. In that unification, the mystery of gravity's origin may finally yield to reason, and with it, the first genuine key to shaping the way. Curvature of reality. Gravity is the oldest of the known forces, yet it remains the least understood. We can describe it, measure it, and predict its effects with exquisite precision, but we cannot fully explain why it behaves as it does. The deeper we probe, the more it seems to defy the framework that governs everything else. Quantum mechanics, the theory that rules the microscopic world, describes forces through the exchange of particles, photons for electromagnetism, gluons for the strong nuclear force, and W and Z bosons for the weak interaction. Each of these mediators fits neatly into the quantum tapestry, but gravity refuses to join them. It stands apart, describing not a field that fills space, but the shape of space itself. This separation has haunted physics for more than a century. Einstein's general relativity explains how mass and energy bend space-time, and how that curvature directs motion. Quantum mechanics explains how matter behaves at the smallest scales. Each theory works perfectly within its domain, yet they are mathematically incompatible. Relativity treats space-time as smooth and continuous, while quantum mechanics reveals a world of uncertainty, where position and momentum cannot both be known, and where reality itself flickers with probability. When we try to merge them, to describe the geometry of space-time as a quantum entity, infinities erupt in the equations. Something fundamental is missing. The search for that missing theory, known as quantum gravity, is not merely an academic exercise. It is essential to understanding the birth of the universe, the interiors of black holes, and perhaps even the future of technology. Wherever gravity and quantum mechanics meet, at the Planck scale, around 10 to the power of -35 meters, our current theories collapse. To control gravity, we must first learn to describe it there, where curvature and quantum fluctuations become indistinguishable. Physicists have proposed several approaches to this problem. The most famous is string theory, which replaces the idea of point-like particles with one-dimensional vibrating strings. Each vibration corresponds to a different particle, and among those vibrations is one that naturally behaves like a graviton, a quantum of curvature. In this framework, gravity is not an external force, but an emergent vibration of the strings that make up everything. String theory also predicts extra dimensions beyond the familiar 3 of space and 1 of time. These hidden dimensions could help explain why gravity is so weak compared to other forces. It might be spreading through those unseen directions, diluting its strength in ours. Another approach, loop quantum gravity, takes a different path. It begins with Einstein's geometry and asks what happens when we quantize space itself. The result is a vision of space-time made not of smooth curves, but of discrete loops woven together into a network. Each loop represents a tiny quantum of area, or volume. Together, they form the scaffolding of reality. In this picture, gravity is the result of how these loops twist and connect. There is no continuous fabric to bend, only a vast web whose links vibrate and evolve according to quantum rules. Both theories share a common message. Space-time is not fundamental. It emerges from something deeper, a set of underlying relationships, patterns, or information that we do not yet fully understand. This idea, though radical, may hold the key to controlling gravity. If the geometry of the universe arises from a network of quantum interactions, then perhaps we could one day manipulate that network. Instead of moving matter to bend space-time, we might rearrange the quantum information that defines it. The challenge lies in verification. Quantum gravity operates at energies far beyond what our instruments can reach. The Planck energy, the scale at which space-time becomes quantized, is around 10 to the power of 19 giga-electron-volts, 1 trillion times higher than what the Large Hadron Collider can achieve. Direct experimentation is impossible for now, but indirect clues may exist. Black holes, with their extreme curvature, act as natural laboratories for quantum gravity. The way they emit radiation, store information, and evolve may reveal how space-time behaves at its limits. Stephen Hawking's discovery that black holes radiate due to quantum effects was a turning point. It showed that gravity and quantum mechanics are not separate but intertwined. The radiation that escapes from a black hole carries information, implying that even the most curved space-time obeys quantum rules. Yet it also creates a paradox. If black holes eventually evaporate, what happens to the information they contained? Quantum mechanics forbids information loss, but general relativity predicts it. Resolving this contradiction has become one of the central quests of theoretical physics. Recent advances suggest that the answer may lie in holography, the idea that all the information contained within a region of space can be described by data on its boundary. In this view, our three-dimensional universe might be a projection of information encoded on a distant two-dimensional surface. This concept, known as the holographic principle, links gravity to quantum entanglement in a profound way. It implies that space-time itself could emerge from the pattern of entanglement between quantum particles. If that is true, then gravity is not a fundamental force at all, but a statistical effect, a kind of thermodynamics of information. The curvature we perceive as gravity would be the large-scale behavior of countless quantum connections. Controlling gravity, then, would mean controlling those connections. It would be like learning to rearrange the microscopic structure of space, changing how information flows and, consequently, how geometry responds. While these ideas remain theoretical, they open new ways of thinking about gravitational technology. Instead of massive machines trying to generate curvature through brute energy, future physicists might engineer entanglement patterns that create localized distortions in space-time. Such control would operate at the level of quantum information, perhaps through advanced forms of computation or coherent matter fields. The first steps toward this vision may already be visible in quantum computing, where the manipulation of entanglement has become a practical science. The convergence of quantum information theory and gravity is more than coincidence. Many researchers now believe that space-time itself is an emergent phenomenon, a dynamic expression of information. This perspective transforms the question of anti-gravity from how do we lift against curvature to how do we change the informational structure that defines it? It shifts the problem from engineering to understanding, from energy to knowledge. But as always, the path from theory to control is long. For every new insight, there are layers of complexity waiting beneath. The mathematics of quantum gravity is notoriously difficult, its predictions nearly impossible to test. Yet every step forward reveals new connections between black hole entropy, holography, quantum entanglement, and the flow of time itself. These are not isolated puzzles, but facets of one hidden truth: that gravity is the geometry of information. If we can learn to read that geometry, we may eventually learn to write it. And when we can write space-time, we will no longer ask how to escape gravity. We will ask what new worlds we might create by shaping it. In laboratories scattered across the world, physicists now search for the faintest hints that quantum gravity leaves behind, delicate traces that might reveal how space-time behaves when it is stretched to its limits. Since we cannot build instruments powerful enough to reach the Planck energy directly, we look instead for its fingerprints in the way the universe behaves on smaller scales. These clues, though subtle, could one day bridge the chasm between Einstein's smooth cosmos and the quantum world's restless motion. One of the most promising sources of evidence comes from the ripples of space-time itself, gravitational waves. When LIGO first detected these waves in 2015, it was not merely a triumph of engineering, but a revelation. For the first time, humanity had heard the vibration of space-time, the echo of two black holes merging a billion light-years away. Those waves carried information about how curvature behaves when pushed to its extremes. As detectors become more sensitive, we may find signs of deviations from Einstein's predictions, tiny quantum distortions superimposed on the classical waves. Each subtle difference could whisper secrets about the underlying structure of reality. Physicists also search for signs of quantum gravity in the behavior of particles and light. High-energy photons arriving from distant gamma-ray bursts, for instance, travel through billions of years of expanding space. If space-time has a granular structure, those photons might scatter slightly or arrive at different times depending on their energy. So far, observations show no such dispersion, suggesting that space-time remains smooth even across unimaginable distances. But the limits of detection are constantly improving, and each new telescope tightens the boundary between what is seen and what might still be hidden. Closer to home, experiments with ultra-cold atoms offer another path. Atom interferometers, which measure how quantum waves of matter interfere after being split and recombined, can detect gravitational differences smaller than 1 part in a trillion. When used to probe the behavior of atoms in free fall, these instruments test one of Einstein's most fundamental assumptions, that all objects, regardless of their composition, fall the same way in a gravitational field. So far, that equivalence has held perfectly, but any deviation would signal a breakdown of general relativity at quantum scales. The absence of a difference is a result in itself. It shows how deeply unified the universe's geometry remains, even when viewed through the lens of quantum uncertainty. At the same time, theoretical models are being tested against the extreme conditions of black holes and the early universe. The cosmic microwave background, the faint afterglow of the Big Bang, may contain imprints of quantum fluctuations that were stretched to cosmic scales by inflation. Patterns in its polarization and temperature could reveal how gravity behaved when the universe was less than a trillionth of a second old. If confirmed, such evidence would link the quantum and cosmic in one continuous story, a proof that the same laws govern both atoms and galaxies. Beyond pure observation, some researchers are exploring analog systems that mimic aspects of quantum gravity. Within superfluid helium, Bose-Einstein condensates, and optical lattices, scientists can reproduce the equations that describe curved spacetime. These experiments, though miniature and metaphorical, allow physicists to test hypotheses about horizons, information flow, and even Hawking-like radiation in the laboratory. When sound waves or light behave as though trapped inside an artificial horizon, they offer glimpses of how curvature and quantum effects coexist. Though these analogues are not true gravity, they let us experiment with its logic. Philosophically, these studies raise profound questions about the nature of reality. If gravity and spacetime are emergent phenomena, then what we experience as geometry is not fundamental. It is an approximation, like temperature or pressure in thermodynamics. Just as temperature arises from the collective behavior of atoms, gravity may arise from the collective behavior of quantum information. This realization would transform not only physics, but metaphysics. It would mean that the universe's shape, its expansion, and even the flow of time itself emerge from patterns of information that evolve according to deeper laws. In this light, the dream of controlling gravity takes on a new meaning. Instead of imagining machines that push against spacetime, we might someday envision devices that alter the informational structure that produces spacetime. A gravitational field would then be not a force to oppose, but a configuration to rewrite. It would be like learning to compose a new melody in the symphony of existence, adjusting how information and energy interact so that geometry follows our design. Yet even as we imagine such possibilities, we must remain humble. The mathematics of quantum gravity is formidable, and its physical interpretation remains uncertain. Each theory, string theory, loop quantum gravity, emergent spacetime, causal sets, holography, offers a different glimpse of truth, but none yet paints the whole picture. Nature may be hinting that our deepest assumption is wrong, that spacetime itself is not the stage upon which reality unfolds, but one of the actors in the play. If that is true, then to control gravity is to participate in the rewriting of reality itself. It would require not just technological mastery, but a new philosophy of existence, one that recognizes the universe as a living computation, a vast network of information in constant transformation. Within that network, energy and geometry are not separate. They are two expressions of the same underlying principle. We already manipulate information through computation and communication. To extend that mastery into the quantum geometry of spacetime would be the ultimate step, the moment when humanity moves from observing the universe to sculpting it. Still, between vision and achievement lies the gulf of understanding. The next generations of experiments, gravitational wave observatories, quantum sensors, high-energy particle detectors, will bring us closer to that bridge. Each new measurement will refine the laws, narrowing the space where mystery hides. Whether the path ends in a grand unified theory or a new understanding beyond our imagination, it will change our view of what gravity truly is. In the end, quantum gravity is not merely a problem to solve, but a doorway. On one side stands our familiar world, where mass pulls mass and space bends gently under weight. On the other side lies a realm where geometry and information are indistinguishable, where space and time are woven from probabilities, and where the curvature of reality can, perhaps, be shaped by will. To step through that doorway is to redefine what it means to understand. At the frontier where quantum gravity begins to take shape, the question no longer sounds like, what is gravity, but what creates it? If space and time are not the foundations of reality, but consequences of something deeper, then gravity may be a reflection of an invisible order, the organization of information and energy at the smallest conceivable scale. To imagine controlling gravity, we must first imagine touching that order, reshaping the pattern from which geometry itself arises. It is an idea so immense that it borders on philosophy, yet it grows naturally from the physics we already know. Every sign points toward gravity being an emergent phenomenon. Entanglement, the strange quantum linkage that connects particles across distance, seems to play a central role. In recent years, physicists studying the holographic principle have uncovered an astonishing connection. The structure of entanglement in a quantum system determines the curvature of the space that surrounds it. In other words, the more entangled a system's components are, the smoother and more continuous the emergent geometry becomes. If those entanglements weaken or break, the geometry itself begins to tear. This insight suggests a new picture of spacetime, not as a pre-existing container, but as a web woven by relationships. The universe holds together because its quantum parts remain connected. Gravity, in this interpretation, is the expression of those connections seeking equilibrium. If the balance of entanglement changes, curvature changes too. It is a vision of reality that replaces substance with structure, where the strength of relationships defines the shape of the cosmos. From this view, the manipulation of gravity becomes a question of information control. If we could alter how quantum states entangle, we might reshape the geometry they generate. This is not a fantasy, but a mathematical implication of the holographic approach. The same equations that describe black holes, where information seems to vanish yet somehow re-emerges, also describe how space-time responds to shifts in entanglement. A sufficiently advanced civilization, or a far future version of humanity, might one day learn to engineer such entanglement deliberately, tuning curvature like a musician tuning the resonance of a string. This might sound abstract, but we already practice primitive forms of it in laboratories. Quantum computers manipulate entanglement patterns to perform computations that no classical system could match. The difference lies only in scale. A quantum processor rearranges information within a few hundred qubits. A gravitational engineer, in theory, would rearrange information across billions. The principles, however, may be the same. Both depend on coherence. The ability of quantum states to remain stable long enough for interference patterns to build. If coherence could be maintained at macroscopic levels, the boundary between quantum systems and geometry might begin to blur. Some physicists speculate that gravitational control could someday emerge as a byproduct of quantum technologies. As quantum computers become larger and more coherent, the entanglement structures they create will grow increasingly complex. In theory, there is no reason those structures could not have gravitational effects, however tiny. The energy densities involved would be infinitesimal, but so are the ripples that travel through space-time when two distant black holes merge. The principle that information flow and curvature are linked implies that any system manipulating information at sufficient density might influence geometry itself. Of course, the energy requirements for meaningful curvature remain immense. Einstein's equations still dictate that to bend space-time significantly, enormous amounts of energy are required. But if gravity truly emerges from information, there may be clever ways to simulate its effects with much less power, the same way a hologram can produce a three-dimensional image without a physical object. Instead of creating curvature through mass, we might one day create it through computation, by organizing information in patterns that space-time naturally interprets as gravity. This idea leads to a radical possibility that the universe itself might already be a computation running on the logic of quantum information. In such a framework, controlling gravity would be equivalent to rewriting part of that code. It would mean gaining access to the operating system of reality, altering how energy, matter, and geometry relate. Such control would not come from brute force, but from understanding, from learning how the smallest units of existence give rise to the largest. Even within this visionary framework, limits remain. The laws of thermodynamics apply to information as they do to energy. Entropy, the measure of disorder, ensures that no manipulation of curvature can be perfectly efficient. To change the geometry of spacetime, one must expend energy and increase entropy elsewhere. The universe keeps its books balanced. Any future gravitational technology would have to work within those balances, trading one form of order for another. In this sense, the dream of gravity control becomes not a rebellion against physics, but a negotiation with it. If such mastery were ever achieved, its implications would be staggering. Control over curvature would mean control over time. A device that could generate a gravitational field strong enough to slow clocks could, in principle, allow temporal manipulation, not time travel in the cinematic sense, but the ability to stretch or compress the flow of time within regions of space. Communication, propulsion, and energy generation would all be transformed. A gravitational lens engineered deliberately could focus light across interstellar distances, linking worlds in real time. A localized warp bubble could enable travel without motion by sliding the surrounding spacetime itself. Yet the ethical and philosophical consequences might dwarf the technological ones. If gravity defines the structure of reality, then to command it would be to edit existence. Every particle, every life, every memory is shaped by curvature. To alter that curvature is to change the rhythm of the universe. Such power would demand wisdom equal to its reach, the understanding that creation and destruction are merely opposite sides of the same geometry. In the end, the search for quantum gravity is not only about finding equations that unite physics, it is about discovering what the universe truly is, a network of energy, information, and meaning woven together by laws that are at once mathematical and profound. To understand gravity fully is to glimpse the logic of creation itself. Whether or not humanity ever learns to command it, the pursuit alone brings us closer to the source of reality, the moment when geometry, information, and consciousness first became one. When that understanding finally arrives, gravity will no longer be a mystery to overcome. It will be a language to speak, the language of existence written in curves, vibrations, and relationships. To master that language is to master reality itself. The idea that space and time can bend, twist, and stretch is no longer poetic imagery. It is the literal truth of the universe. Gravity is not a force that pulls across a distance. It is geometry in motion, shaped by energy and mass. When physicists speak of bending space-time, they speak of sculpting the fabric of existence itself. To imagine controlling gravity, then, is to imagine engineering curvature, learning to mold the structure of reality as easily as we now mold light or sound. For most of human history, such an idea would have been indistinguishable from myth. But modern physics allows us to ask it seriously, to write equations that describe it, and to wonder whether those equations could ever be more than mathematics. Einstein's general theory of relativity provides the blueprint. It shows that mass and energy tell space-time how to curve, and space-time tells mass and energy how to move. These equations have solutions, mathematical worlds that describe how curvature behaves under different conditions. Some of these solutions correspond to familiar objects like stars and black holes. Others describe more exotic geometries, ones that appear to break the usual rules of distance and time. They are windows into possibilities that nature may never realize on its own, but which mathematics allows us to imagine. It is among these solutions that the first concepts of gravitational engineering emerge. One of the most famous is the warp drive, a theoretical construct that reshapes spacetime to allow motion faster than light without technically breaking the cosmic speed limit. In 1994, the Mexican physicist Miguel Alcubierre proposed a solution to Einstein's equations in which a bubble of spacetime expands behind a spacecraft and contracts in front of it. Inside the bubble, the ship remains stationary relative to its local space. It does not move faster than light within the bubble, yet the bubble itself rides a wave of geometry that can travel any distance in arbitrary time. The idea astonished the scientific community. It seemed to offer a loophole in the laws of relativity, a way to cross the stars without acceleration or time dilation. But the equations carried a catch. To generate such a warp bubble, one would need negative energy density, a kind of matter that curves space-time in the opposite direction from normal mass. No known substance possesses such a property. Ordinary energy, no matter how intense, bends space-time inward. Negative energy would bend it outward, stretching space behind the bubble and squeezing it ahead. Some quantum effects, such as the Casimir vacuum between two closely spaced plates, can produce tiny regions of negative energy, but the amount is microscopic. The Alcubierre drive would require energy equivalent to many suns concentrated in a region smaller than a starship. Even if it could be created, it would be catastrophically unstable. A single fluctuation could collapse the bubble or tear it apart. Despite these obstacles, the warp drive remains valuable as a thought experiment. It shows that Einstein's equations do not forbid faster than light travel outright. They only make it extraordinarily difficult. By playing with geometry, we can conceive of paths through space-time that bypass conventional limits. The equations themselves invite imagination. They describe a universe far more flexible than intuition allows, a universe in which space can flow, expand, and fold back upon itself. Another class of solutions reveals an even stranger possibility: wormholes. These are tunnels through space-time connecting distant regions, perhaps even different universes. The concept first appeared in the 1930s when Albert Einstein and Nathan Rosen found a mathematical bridge between two black holes, now called an Einstein-Rosen bridge. Later studies showed that such bridges would collapse instantly under their own gravity, closing before anything could pass through. To keep them open would again require negative energy, exotic matter with repulsive curvature strong enough to counteract collapse. The equations describing traversable wormholes have been studied extensively, and their geometry is clear. Two mouths connected by a throat, each existing in a different location or time, could in principle allow instantaneous travel or even time loops. The mathematics does not forbid them, but the conditions they demand seem impossible to realize. No known process can generate the required negative pressure or stabilize the structure against quantum fluctuations. A wormhole, if it could exist, would act like a gravitational capacitor, storing enormous energy within its throat. Any imbalance would destroy it in a burst of radiation. Still, the concept of a wormhole has become more than speculation. It serves as a bridge between relativity and quantum physics. Recent studies suggest that certain types of quantum entanglement may be equivalent to microscopic wormholes, that particles linked across space are, in some sense, connected by tunnels of geometry too small to see. This idea, often summarized as entanglement equals wormholes, offers a remarkable unification of concepts. It implies that connectivity in spacetime and connectivity in quantum information are the same phenomenon viewed from different angles. If this is true, then controlling entanglement could one day allow us to control geometry itself. perhaps creating the first engineered wormholes at quantum scales. Other theoretical constructs push geometry even further. The concept of a closed time-like curve, a path through space-time that loops back on itself, arises naturally in some solutions to Einstein's equations. The Kerr metric, which describes a rotating black hole, allows such loops near its ring-shaped singularity. In theory, an object traveling through this region could return to its own past. But again, stability and energy conditions intervene. The slightest disturbance could destroy the loop or trap any traveler in chaos. Time travel, though mathematically permissible, remains physically unattainable under known laws. What these exotic solutions teach us is not that we can already build warp drives or wormholes, but that the universe's geometry is not fixed. Space and time are dynamic, capable of being stretched, compressed, and connected in ways far beyond ordinary experience. The same mathematics that predicts black holes also predicts expansion, contraction, and connection. The difference lies in the sign of energy and the balance of curvature. If we could ever produce or manipulate negative energy safely, we would step beyond the bounds of current physics into a new domain of engineering, the deliberate shaping of space-time. The difficulty lies in scale. To curve space-time by even 1% within a room-sized region would require energy equivalent to the mass of a planet. To create a warp bubble a few meters wide would demand more energy than exists in the visible universe. These numbers are not exaggerations. They follow directly from the stiffness of space-time, from the enormous constant that couples energy to curvature in Einstein's equations. Nature herself only achieves such feats through the titanic energies of stars, black holes, and cosmic expansion. Yet physics often advances not through brute force, but through cleverness. Just as we learn to simulate weight with acceleration and to mimic gravitational lenses with magnetic fields, we may someday learn to imitate curvature through indirect means. Plasma fields, coherent light, or quantum condensates might one day produce geometric effects at microscopic levels. Even the smallest success, a measurable deviation from Newtonian gravity created in a lab, would mark a revolution. It would be the first demonstration that space-time responds to manipulation. In the meantime, the study of theoretical curvature reveals the boundaries of what is possible. It tells us that the laws of the universe are generous in imagination, but strict in practice. They allow extraordinary geometries, but demand impossible energies. They tease us with the shapes of future technologies, while reminding us that nature enforces her limits through mathematics. The same equations that make warp drives conceivable also make them unreachable, at least for now. But history suggests that impossibility is often temporary. When Maxwell wrote the equations of electromagnetism, no one imagined radio or radar. When Einstein wrote his field equations, no one imagined that a century later we would detect gravitational waves. Theoretical constructs that once seemed abstract have a way of becoming real when understanding deepens. The mathematics of bending space-time may someday follow that same path, guiding us toward new tools that work not by fighting gravity, but by joining it, by shaping curvature as naturally as wind shapes a sail. If that day comes, humanity will face questions not of possibility, but of purpose. What would we do with the power to reshape space-time, to create regions where time flows differently, or where distance collapses? To bend the universe's geometry would be to wield creation itself. Such mastery would demand an ethics as profound as the physics behind it. The universe may be patient enough to give us the knowledge, but whether we will have the wisdom is another matter. For now, the equations remain on paper, elegant and untamed. They show that space can bend, twist, and connect, that the structure of reality is a living thing. They remind us that every step we take toward understanding gravity brings us closer not just to technology, but to the heart of existence itself. When we study the bending of space-time, we are not merely solving equations. We are learning how the universe breathes, Long before humans dreamed of bending spacetime, they discovered how to imitate gravity's touch. The pull that binds us to the Earth is more than a force. It is a sensation. Weight, pressure, motion. When gravity itself cannot be changed, these sensations can still be recreated. The first astronauts, floating inside their capsules, understood that weightlessness was not the absence of mass, but the absence of acceleration. They felt it in the drift of their tools, in the slow rotation of their bodies. And from that experience grew a simple revelation. Acceleration and gravity are the same story told in two languages. Einstein called it the equivalence principle, and it remains one of the most profound truths in physics. In any small region of space, the effects of gravity are indistinguishable from those of acceleration. A person standing in an elevator cannot tell whether they are being pulled downward by the Earth or pushed upward by motion. Both create weight. Both curve the paths of falling objects. The universe itself does not care which causes which. Only that motion and geometry are inseparable. This insight gives us the first real tool for simulating gravity. Rotating habitats, the classic vision of life in space, are built upon this principle. A wheel spinning through the void creates its own downward direction. The faster the rotation, the stronger the apparent gravity at its rim. Astronauts walking along the inner surface feel pressed toward the hull, though no planet lies beneath them. This is centrifugal force, an imitation of gravity born from motion, not mass. It requires no mysterious field, only the geometry of circular acceleration. Though imperfect, it demonstrates how easily perception bends when acceleration replaces curvature. In spacecraft design, the same principle defines comfort and orientation. Even short bursts of thrust produce momentary weight. A ship accelerating at 10 meters per second squared would generate an artificial gravity nearly equal to that of Earth. The problem, of course, is sustaining it. Rockets burn fuel, and fuel runs out. Continuous acceleration at such a rate would demand impossible energy reserves. Still, the principle remains sound. If humanity ever builds engines capable of constant thrust, the long journeys between stars could feel as natural as standing on solid ground. These mechanical imitations remind us that gravity is a matter of reference. To fall freely through a gravitational field is to feel no weight at all. Astronauts orbiting the Earth experience microgravity, not because gravity has vanished, but because they are perpetually falling. Their path curves along the planet's curvature. Their motion matches the pull exactly, turning descent into endless flight. Gravity never disappears. It only changes the stage on which we move. Scientists have tried to go further, to mimic not just the feeling of gravity, but its measurable effects on matter and light. High-energy, plasma experiments, for instance, create fields so intense that they distort electromagnetic waves in patterns resembling gravitational lensing. In these miniature analogues, light bends as if passing near a massive body, though no mass is present. The geometry of the plasma, shaped by magnetism and temperature, performs the trick. It is not true curvature, but it hints at the possibility of engineering environments that behave as though space-time itself were warped. At even smaller scales, quantum systems allow subtler simulations. In Bose-Einstein condensates, clouds of atoms cooled to near absolute zero, researchers can reproduce equations that mirror those governing black holes. When sound waves travel through such condensates, they encounter horizons beyond which they cannot escape, much like light trapped by a singularity. These laboratory sonic black holes radiate energy in patterns that mimic Hawking radiation. They prove that geometry and energy can be recreated in surprising ways, that the language of curvature can be spoken even by ordinary matter under extraordinary conditions. Still, these proxies are only shadows of the real thing. They cannot bend space-time itself, they only copy its mathematics. Yet imitation is often the first step toward mastery. The Wright brothers did not understand aerodynamics fully when they first flew. They imitated the flight of birds. Likewise, physicists imitate gravity in controlled conditions to learn how it responds, to see which aspects are essential and which are artifacts of scale. Each experiment adds one more clue to the puzzle of how spacetime behaves when it is pushed, twisted, or vibrated. Some of the most promising research comes from the study of gravitational waves. These are not analogues, but true movements of spacetime, generated by massive bodies in motion. The detectors that captured them, long tunnels of laser light, sensitive to distortions smaller than a proton, are the first machines to interact directly with the fabric of the universe. Though they cannot control those waves, they can read them, measuring the universe's curvature in motion. In doing so, they mark the transition from observing gravity's effects to detecting its structure. It is the first whisper of communication with geometry itself. Perhaps one day, such detection will become direction. A civilization that learns to generate gravitational waves deliberately could transmit information through spacetime, bypassing the need for electromagnetic signals. These waves cannot be blocked or absorbed. They travel through everything. The same instruments that now listen to black holes could someday serve as the speakers of a gravitational language. It is a remote vision, but no longer pure fantasy. The first steps have already been taken. For now, we work with substitutes: rotation, acceleration, plasma, and condensates, each an echo of the real phenomenon. They teach us that gravity is not unique in its behavior, but part of a spectrum of geometric effects that arise whenever energy moves through space. The more precisely we understand those relationships, the closer we come to genuine control. The dream may not be to nullify gravity, but to weave its patterns, to design trajectories and environments where its influence becomes a tool rather than a limitation. Humanity has always built its progress on imitation before invention. We learn to fly by copying birds, to swim by watching fish, and perhaps we will learn to bend spacetime by observing the universe itself. The line between simulation and reality will blur until one becomes the other. Every rotating station, every accelerating ship, and every quantum experiment is a rehearsal for that moment, the day we stop resisting gravity and begin composing with it. Nature has already mastered what humanity can only imagine. Across the cosmos, gravity is not a challenge to overcome, but a language already spoken fluently. Every star, black hole, and galaxy is a sculptor of space-time, shaping the universe through the weight of its own existence. If we wish to control gravity, we must first learn from these natural engineers who bend the fabric of reality without effort. The black hole is gravity's ultimate expression, a place where space-time curves upon itself until no light can escape. What remains is not an object, but pure geometry, a region where mass and energy have become one with curvature. The event horizon marks the limit of visibility, beyond which time and space exchange meaning. Everything that crosses it falls not into a void, but into the deepest fold of existence. Around black holes, the rules of reality reveal their flexibility. Time slows, light bends, and energy streams outward in jets that stretch across galaxies. In their silent motion, black holes demonstrate what it means to control gravity, not resist it, but become it. Neutron stars show another side of gravitational mastery. These collapsed remnants of massive stars are small enough to fit inside a city, yet heavier than the sun. Their crusts hold oceans of atomic matter compressed to unimaginable density. A pebble dropped on a neutron star would strike with more force than 1,000 nuclear bombs. And yet, out of this violence comes beauty. Many neutron stars spin hundreds of times per second, sweeping beams of light across space like cosmic lighthouses. Their extreme curvature and magnetic fields generate order from collapse, gravity and motion working in harmony. Even light itself feels gravity's hand. When it passes near a massive galaxy, its path bends as though it were refracted by an invisible lens. This phenomenon, called gravitational lensing, allows astronomers to see objects otherwise hidden, magnified by the geometry of spacetime. Nature builds telescopes out of curvature. Galaxies act as mirrors of gravity, showing that mass and light can cooperate to reveal the unseen. If humanity could ever shape such lenses deliberately, we could turn gravity into an optical tool, focusing starlight across billions of light years. The cosmos also demonstrates repulsive gravity, the opposite of attraction, through dark energy, the mysterious pressure driving the universe's expansion. It stretches spacetime itself, accelerating galaxies away from one another. While black holes compress space, dark energy expands it. The universe balances these two forces, attraction and repulsion, in a cosmic dance that defines its structure. The same equations that describe one also predict the other. Somewhere within that symmetry may lie the secret to gravitational control. Perhaps the most astonishing natural demonstration of spacetime manipulation comes from rotating black holes. According to Einstein's theory, their spin drags spacetime around with them, twisting it into vortices. Anything nearby is caught in that whirlpool of geometry, forced to move even if it stands still. It is the ultimate example of moving space itself, propulsion without motion. A civilization that could harness even a fraction of that effect could travel without engines, propelled by spacetime's own rotation. Nature's mastery humbles us. What we call impossible, the universe performs effortlessly. Every orbit, every lensing arc, every collapsing star is proof that gravity can be guided, but only by energies far beyond our reach. Still, the lesson is clear. Control of gravity does not mean defying it, but aligning with the same principles that power the stars. Nature's examples are not fantasy, they are instructions written in the language of curvature. When we look at the night sky, we are not merely seeing points of light. We are witnessing experiments in gravitational design running for billions of years. The cosmos is already the engineer we aspire to be. Our task is to learn its methods, to read its geometry, and one day, perhaps, to join in its creation. Every revolution in science begins quietly. The control of fire began with sparks. The control of electricity began with amber rubbed by hand. And the control of gravity, the most elusive force of all, has already begun, not with grand machines, but with light beams, cold atoms, and patient observation. Humanity is still far from sculpting spacetime, yet for the first time in history, we can measure its movements, record its vibrations, and test its boundaries. When the detectors of the Laser Interferometer Gravitational Wave Observatory captured the faint ripple of spacetime in 2015, the universe itself seemed to whisper. Two black holes had collided 1 billion light-years away, shaking the very geometry of reality. That vibration arrived on Earth so weak that it stretched space by less than 1,000th of a proton's width. Yet it was enough. Two lasers, separated by kilometers, flickered in perfect unison as the wave passed. For the first time, humanity heard the sound of gravity in motion. This was not control, but communication. The detectors did not resist or redirect space-time. They simply listened to it. But in that act of listening came the beginning of mastery. To measure a thing so delicate is to understand its nature, and to understand is to prepare for control. Elsewhere, quantum physicists work on a smaller scale. They cool atoms to near absolute zero, suspend them in vacuum, and let them fall. As they fall, their quantum waves interfere like ripples meeting in water. The interference pattern shifts ever so slightly under gravity's pull. By studying those shifts, scientists can measure the local gravitational field with astonishing precision, so sensitive that they can detect underground tunnels, hidden masses, or even the slow drift of tectonic plates. Each atom becomes a sensor of curvature, a grain of geometry revealing the shape of space itself. These quantum measurements are the first footsteps of gravitational technology. They show that gravity can be mapped with detail once thought impossible. In time, those maps may become blueprints, guiding how we might one day manipulate curvature. For now, they reveal that gravity is dynamic, alive, and measurable at scales small enough to fit on a laboratory table. Some researchers have even tried to coax gravity into new forms. Rotating superconductors, high-current plasma rings, and other exotic systems have been tested for minute anomalies. Hints that spacetime might respond to unusual energy states. So far, none have shown clear success, but the persistence of such experiments matters. Each test refines the limits of what is possible. Each failure narrows the mystery. The space agencies of the world are joining the search. Satellites like Grace and GOSI orbit the planet, measuring its gravitational field with exquisite accuracy. They see oceans shift, glaciers melt, and mountains breathe under the motion of the Earth's crust. Gravity is not a single pull, but a living map, changing moment by moment. By watching it evolve, we learn how to measure curvature as a function of time, a skill essential for any future attempt to shape it. The next step will come from gravitational wave astronomy's successor, the Laser Interferometer Space Antenna, a triangle of spacecraft millions of kilometers apart. It will listen to deeper, slower ripples, the heartbeat of galaxies and black holes. These signals will teach us how curvature carries energy, how it propagates, and perhaps how it can be excited deliberately. When we understand how the universe plays its gravitational music, we may learn to compose our own. True control of gravity may still be far away, but its language is no longer silent. We have begun to read it, through light, through motion, through the trembling of spacetime itself. The leap from reading to writing is only a matter of patience. Every act of measurement brings us closer to influence. Every vibration we detect brings us nearer to creation. And perhaps someday, centuries from now, the quiet hum of a lab laser or the whisper of falling atoms will be remembered as the first time humanity reached out and gravity for the first time answered. There will come a day, perhaps centuries or millennia from now, when humanity will look back on the age of rockets and falling apples as the dawn of something far greater. The moment we first began to suspect that gravity could be not only endured, but shaped. Every discovery, from Newton's falling fruit to Einstein's bending spacetime, has moved us closer to that realization. Each experiment that measures a gravitational wave or detects a quantum fluctuation brings us nearer to a truth almost impossible to grasp, that the universe is not fixed, and that its geometry may one day be written like a language we can speak. If that day arrives, gravity will no longer be a barrier, but a medium. Space and time themselves will become the materials of engineering. A civilization that can control curvature would not need engines in the conventional sense. It could travel by sculpting the space between destinations, compressing the distance, or sliding along a wave of geometry. Propulsion would give way to navigation, not through space, but through space-time itself. Ships could ride ripples of curvature the way surfers ride waves, their motion requiring no fuel, only precision in shaping the fabric beneath them. Such technology would transform more than travel. Communication would transcend light. Gravitational waves can pass through stars, planets, and even black holes without obstruction. A civilization that can generate them on demand could speak across galaxies instantly, sending messages encoded in the rhythm of space-time. The same principle could allow energy transfer on unimaginable scales, using curvature itself as the conduit. The universe would become a network not of signals or particles, but of pure geometry, a web of vibrations through which information flows as naturally as light through glass. Yet the most profound consequence would be temporal. Gravity defines the rate at which time flows. In stronger curvature, time slows. In weaker curvature, it accelerates. To control gravity is to control time itself. Imagine laboratories where time is stretched to allow centuries of computation in a single external day, or habitats where subjective centuries pass while only years elapse beyond. The mastery of curvature would be the mastery of duration, perception, and history. It would not merely move us through the cosmos, it would change what it means to exist within it. But such mastery comes with a paradox. To reshape spacetime is to edit reality. Every gravitational field, every curve, every ripple defines how energy and matter interact. Altering it carelessly could ripple consequences across vast distances. The ethics of gravitational technology would eclipse any moral challenge humanity has ever faced. It would demand restraint born of understanding and wisdom equal to its reach. Those who control time and space would, in effect, control causality, the order of events, the heartbeat of the universe itself. Still, the dream persists because it reflects something deeper than ambition. Gravity is the geometry of existence, and humanity has always been drawn to the act of shaping what surrounds it. We sculpt stone into temples, light into circuits, and now space into data. The control of gravity would be the final extension of that impulse, the transition from adapting to the universe to participating in its design. To some, that sounds like hubris, to others, destiny. The truth may be both. The path to that future will not be a single discovery, but a continuum. It will pass through generations of physicists refining theories of quantum gravity, engineers building instruments that measure curvature with atomic precision, and thinkers who redefine what it means to manipulate reality. Already, hints of this path exist. The merging of quantum information theory with space-time physics shows that geometry may be no more fundamental than the patterns of data that underlie it. When we master those patterns, when entanglement becomes a tool rather than a mystery, gravity itself will yield. Perhaps the first act of gravitational engineering will not be grand. It may begin as a ripple, a laboratory anomaly, a localized curvature produced intentionally for the first time. That moment will mark the end of one era and the beginning of another, the instant when humanity moves from describing the universe to participating in its architecture. From that point on, every boundary will shift. Distance will lose meaning, time will become negotiable, and energy will flow according to geometry designed by intelligence. And yet, amid all that power, one truth will remain. Gravity is not an enemy to conquer, but a companion to understand. It is the rhythm that keeps the cosmos coherent, the bond that ties energy to form. To control it without reverence would be to forget the beauty that made us seek it in the first place. The universe bends gracefully because it obeys harmony. Our task will be to join that harmony, not to disrupt it. In the final vision of this long pursuit, we stand not as masters of nature, but as co-creators within it. The stars no longer burn beyond reach, but shine within the geometry we help to shape. The flow of time becomes a canvas for thought, the curvature of space a medium for art and science alike. Gravity, once the symbol of inevitability, becomes the instrument of freedom, the means by which we transcend the limits that once defined us. And when that day comes, the first step will not feel like triumph, but awe. We will realize that controlling gravity was never about escaping the universe, but about understanding it so deeply that we could move in rhythm with its design. Gravity is not merely a force to overcome, it is the shape of reality itself. And when we finally learn to sculpt that shape, we will not just travel across the stars. We will rewrite the geometry of existence, joining the cosmos as both its observers and its creators.